But now I'll turn it over to Rob Hopsapian, who's going to speak on microgrid design evolution using resilience framework. Rob, whenever you're ready.
Thank you, Mike. Thanks, Mike and Aaron and FLC for organizing and giving us this opportunity. I'm going to give a quick overview of our microgrid design evolution and the approach that we have taken over the years in order to go ahead and achieve the last project that I'm going to talk about. This is part of the Department of Energy's grid modernization project, and the number listed over here is the number of the projects that are helped build the current project that we're working on. One of it is the Grid Modernization 101 project, which is metrics-oriented, that help us identify the metrics. And in this case, we're looking at resiliency metrics. And I'll talk about a little bit on the GMLC 1.39, how do we use the resiliency metric approach and how we're taking the multidimensional approach for resiliency in this upcoming project. We also have done a project for the CEC, California Energy Commissioner, for a BLR Red Cross evacuation, where it used a digital blueprint approach, where we created a digital blueprint of the microgrid, and we did a hardware in the loop and controller hardware in the loop of the design and all the controller evolution prior to the deployment. And we learned a lot of this hardware in the loop and real-time simulation and modeling of those controller and controller evolution, rapid prototyping of the controller prior to the deployment. And the other project is a run-of-the-river project that we're doing right now for the Department of Energy, where we learn from it how do we leverage short-term storage in a form of rotational inertia in order to allow us to do stability analysis and allows us to do a quick reconfiguration in those microgrids. So those are the list of the projects listed over here, and one additional one we have over here is part of this project. We also have Sandia National Lab that also participated in the cybersecurity aspect of the communication side of the microgrid. As we start tying those devices together, what are the cybersecurity aspect of it, and they're part of the team in developing that. So here's the list of the 5 projects. First of them is the pump storage project that allowed us to look at the rotational inertia of a machine and how to take advantage of the short-term inertia in the microgrid. Second project is a rapid prototyping of the controller development. So we bring in the controller and the vendor, and we'll develop the controller in live against the components prior to the deployment. Third project we have is a next generation microgrid for the West Coast evacuation route, which is the project that we actually used in order to demonstrate the controller hardware in the loop and hardware in the loop approach prior to the deployment and the training the staff prior to deploying in the field. And the other project is a grid modernization 1.39, which is use smart reconfiguration. Most microgrids will go dark before you reconfigure it. In this project 1.39 is one of the first projects that we reconfigure the microgrid in the event of a fault without going dark. And the way we're able to do that is by taking advantage of the rotational inertia of the system itself, and allows us to do the smart reconfiguration and islanding of the system. And the fifth project is the run-of-the-river project, which is taking into account energy storage in order to allow us to do reconfiguration. And as a result of those 5 projects is the project that we're going to talk about is what we call is the RADIANCE project, which leverage all the above 5 projects. In this project, we're using a multidimensional resiliency metrics approach in order to design the resiliency by design system. So we're baking in the resiliency of the microgrid as part of its design. Again, a quick overview of the pump storage project. This was a joint project between Argonne National Lab, NREL, and Idaho National Lab, working with the University of Texas at Austin, where we looked at the rotational inertia of the system, which we calculated in real time the hydrodynamics and the rotational inertia as well as the electrical dynamics at the same time in order for us to better understand the interaction that allow us to utilize that in our design and reconfiguration. The next one is the rapid prototyping of the controller development. In this case, it was a joint project with the Siemens R&D group and Washington State University, where we developed a search microgrid digital blueprint in a real-time simulation, and we created an environment allowing us to develop the microgrid controller, rapid prototyping it, and design and developing the controller itself as we're testing it against the microgrid environment and validating it. And in this case, with this integrating the controller hardware in the loop or hardware in the loop of the devices, showing it here where we took the source microgrid from the previous project, and on top of it, we built the communication layer. So in this case, we had a digital blueprint of the microgrid itself. We actually physically had the controller that was being developed as part of controller hardware in the loop. And to it, we had the hardware in the loop of devices that were actually hanging off the microgrid. And with it, we simulated the communication layer on top of it. So we have the power system as well as the communication system and layer simulated on the same real-time simulation along with its hardware. Once we had those lessons learned and the approach, the next project we implemented on is the Red Cross evacuation for the CEC project, which was partnered with PG&E and Tesla, and Siemens was the microgrid controller vendor for this one. And in this case, we had the digital blueprint environment, and we actually took the hardware and the controller development of the microgrid controller was developed on the same digital blueprint, and all the hardware and the controller that was represented in the field was represented in a control lab environment that allowed us to test its controller functionalities and the behavior and operational scenarios of the microgrid controller prior to the deployment. And once the system was designed and fully operational, we brought in the operators and had them actually sit down in front of this microgrid and test it and run it as if it's a real system and test it and validate it. And the next best thing for this training environment was actually doing the training in the field on the actual system, where in this case they were doing it on a digital blueprint with the actual hardware and behaving and acting as if it's the real system. The last project from the grid modernization is the 1.39. In this case, we used the smart reconfiguration here, where we combine the rotational inertia of the hydro as well as the microgrid controller and combine them into one project, would allow us to take advantage of the storage, the rotation and inertia storage within the system itself in order to help us to do smart reconfiguration without going dark. And the objective of this project is also to provide a generalized roadmap and a guideline for others how to take advantage of this kind of a system, especially when you have inertia in the system in order to do smart reconfiguration and islanding. And this shows a quick overview of the system. It has 4 run-of-the-river plants represented on the top side, and we have the hardware in the loop of the real-time simulation with the switcher relays hardware on connected to the system, and with the micro PMUs as and behaving and acting as if it's the real system, and allowed us to redesign the reconfiguration and the islanding of the system using this approach. And this is the run-of-the-river project, where we're taking the same approach as we did on the previous project, except in this case, we took into account not only the run-of-the-river shown in the lower left side, but also we took into account different kind of storages, whether it rotational inertia, which is a flywheel, or a supercapacitor for fast acting, or batteries for a long-term energy. So we have the combination of those storages along with the run-of-the-river in order to allow us to provide inertia and stability for the system. And the project was between the hardware in the loop side of the project was done at INL. We also teamed up with Argonne National Lab and NREL for providing the generator information. So all these lessons learned from all this previously mentioned project allowed us to design and model the project that we're working on right now, which is the RADIANCE project in Alaska, where it takes into account a resiliency metrics approach for the design. And what you see on the right is the number of organizations that are involved in the project. It's Idaho National Lab, PNNL, and Sandia National Lab. And from working with University of New Mexico State, Florida State University, and Washington State University from the academia side. And we're also working with City of Cordova, Siemens for their energy storage optimization tool, and Alaskan Village Co-op. And the objective of this system is to design a microgrid that allows us to use multidimensional resiliency metrics in a design and taking into account the hardware in the loop and controller in the loop approach in order to minimize the risk of the deployment. And again, here's how the organizations are tied with each other with the focus of doing a resiliency by design approach as we're designing the system. And the focus of the project is, first, is having a resiliency metric approach for the design, where we created a baseline and we measured the system as we're designing and its resiliency. And I'll have a slide here that talks about the resiliency approach on this project. And it uses multiple microgrid, which uses a nested or zonal type approach of microgrid that divides the microgrid into multiple zones and areas that we can see, taking into account the smart reconfiguration and islanding in order to increase the resiliency by keeping the critical loads up, and also taking into account the cybersecurity architecture of the system. And again, with all this, by doing a field validation in a controlled lab environment and providing a training environment for the operators prior to deployment. This is the multi-tier resiliency approach. That resiliency in this case is a function of the anticipation, the withstand, and the in order to compute the resiliency metrics itself, and also take into account the real-time input information such as weather information, avalanche information, or weather conditions, takes into account historical data and the probabilistic analysis data, and uses all this information in order to compute the real-time resiliency metrics and makes a decision based on these resiliency metrics how to reconfigure the system. So if you have a critical load such as a hospital or a command and control center, by looking at all the probability and the historical and the real-time data, it will make the optimum decision in order to decide how to reconfigure the system in the event of a fault and make sure that system is up and running. This is the deployment for the site. It's in Cordova, Alaska. It uses two run-of-river projects showing on the left and right side of the map. And the lower side is where they have the city, which they have a diesel generation, and takes into all those generation in designing the microsystem. Again, this is the teams that are working together and how the interaction between the team, and look forward in the future to provide you with more detail on this the system and this approach. Thank you very much.